Mr. Daniel is Director of Marketing and Strategic Initiatives at Mastercam India. Coming with an engineering background, Mr. Daniel is student and alumnus from the Government Toolroom Training Centre. He has professional experience of more than 2 decades. Prior to Mastercam, he was associated with Delcam for a decade. He is now also associated with UAY project for additive and subtractive manufacturing research at IIT Bombay. Today, Mr. Daniel will share his insights on advancements in hybrid manufacturing and robotic machining using modern CAD/CAM systems. So please welcome Mr. Daniel.
Good evening. Thank you, Ms. Darshana. Good evening, Mr. Gopal Krishna. Uh, Learned panelists, happy to join Mr. Pritesh Singh again. I think this is the second time we both are on the same panel discussion, and he has some amazing insights which he keeps offering on these forums. And I've particularly found your presentation quite insightful, Mr. Singh, and I thought I'll convey as much during the meeting today.
Thank you.
Thank you, OEM Update, for inviting us. After this back-to-back presentations on the industry foresight, industry insights of the future, and Mr. Doraiswamy's wonderful presentation on farming automation, I would like to speak about a very hot technology, which is what it's known as currently in our circles, which is additive manufacturing, hybrid manufacturing, and also some very interesting use cases for robotic manufacturing. So I'm assuming that the delegates who are present here today have some information on these innovative manufacturing processes, which are of recent. They are not something which were quite common traditionally. And this I say because I'll start my presentation by giving you an example of roughly 25 years back when I started my learnings in this technology. I was shown a part with a cube and a sphere that was moving freely inside it. And this was what was called as an impossible part to manufacture, because you have a square, you have a cube, and then there's a sphere that's running freely inside it. Of course, it was a trick in machining technologies, and it's a great example as to how what was considered magic or wizardry in about 25, 30 years back can now be manufactured by a 5-year-old. That is how I would like to give an introduction of what the AM and hybrid manufacturing are capable of. Having said that, let me just take you through a journey of what is the promise of additive. It's known by various names. Of course, even 30, 40 years back, you had something called as rapid prototyping, which was used to create polymer parts of components that you would want to, kind of authenticate or verify aesthetically before you put the actual expensive material into production. From there, this rapid prototyping has evolved vastly, and what it offers is the manufacture of impossible or improbable parts, such as the ones you see on the screen. And what makes them improbable or impossible to manufacture using traditional methods are certain aspects. If you can see my mouse that moves on the screen, so look at this part. It's got a lot of conformal cooling inside here within these areas, which would have been otherwise impossible to manufacture using traditional methods. Lightweighting of parts which are bound to be heavier or bulky, such as that you see in this image here, and the chassis of this motorbike here, are examples of where it has progressed. And predominantly, this is inclined towards creating parts that are either improbable to manufacture or which are price prohibitive using traditional systems. And it is geared at largely to have lightweight products, aesthetically pleasing products as well, as this motorbike chassis here. depicts a vast departure from the standard tubular frames that we have seen so far. It's called additive manufacturing, but there are various different mechanisms and different technologies that are a part of this domain. Uh, a few of those are listed here. I will not go through each of them, but they are there rather as a depiction of these seven families of technologies. So wax polymerization was the powder bed diffusion method. You have the binder jet, where you have the binder that is dropped and fuses these products together. There's a material jetting where the material collates together. You have sheet lamination where you have different layers which are then piled together and adhesed together. There's also material extrusion where it's extruded and added on top of the profile that you want to build. And I'll stop at direct energy deposition mechanism because that is predominantly the one that is being used for commercial purposes worldwide, especially in relation to additive and subtractive combined, which is what we call as hybrid machining, hybrid manufacturing. So if I have to explain the hybrid manufacturing philosophy, I would explain it by showing this image on the screen. We all have colored these different drawing books when you're growing up. So there's an outline and you're given different pencils and you're allowed to color between the lines, um, which is what would result in something that you see on the right side, where you have different colors for, different parts of this robot. That is the additive way of doing things, where you take a fine pen and start filling into each of these, bounded regions, and it creates, an image for you. The hybrid methodology is I would take a crayon and scribble roughly over each of these random parts, and then I would use a fine tip needle or a knife, and then carve out only the ones that have overflowed these bounding boxes, and then the result would nevertheless be the same. Um, but the change being that what used to be a very fine process, a very painstakingly long process, perhaps even more expensive, is now replaced by technology that can be quickly scribbled, and you erase out only the bad areas or the unwanted areas of that coloring which went over the lines. Imagine they are in different layers. That is what hybrid manufacturing is. And the beauty of direct energy deposition mechanism is that the equipment or the machine tools are largely similar to what we have seen in our traditional CNC manufacturing world. You have a multi-axis CNC machine. Typically, if it's a very large part, you would find a head-head kind of a configuration. Else, if it's the smaller parts, you would find something as like similar to what you see on the screen here, which is all movements on the table, and then you have the head depositing and cutting material away using the spindle. Here's a short video I'll pause this video for effect because typically machining such a part for aerospace application would have meant that you would have had to cut it entirely from a block of metal and then machined all of these critical areas, leaving these thin-walled sections, which is a challenge in its own field, which is worth probably 2 hours of discussion online. But the beauty of this hybrid manufacturing or the additive manufacturing being that you could do a near knit shape of what is needed and then machine it down to the final elements. So here's a very simplistic example of how we can do things using the hybrid approach. Now, what we see here is an outline of a component, which is essentially a valve. So it's passing from it's a hollow tube, and then there's an opening on top. And if you would have to create this, you would use a complex mill turn application. But in such cases, you could either machine it out of a cuboid, you could machine it out of a cylinder, or you could use the AM principle where you would just take a tube, do the majority of quick production-based machining, and then build the boss on top, which is the pipe-like structure on top, and finally mill it to its precision. Of course, if it's a rough part without a lot of precision, you could leave it at near net shape, which is approximately at the shape that you would desire it to be. But if the application requires it to be precise, and when I say precise, in a few micromillimeters, which could range between 5 microns to 20 microns or 50 microns, for example, you would then need to finish it with a machining process. And the workflow is that it starts with the CAD model, which is the base of it all. You deposit material for the first stage or the first structural part of your component, and then you finish machine it to what is required, and then you further deposit material for the additional part of it, as you'll see in step number 4 here, and finally machine finish that as well to get the final component. This has been proven to be more efficient, more practical, and more in line with the transition from traditional machining to adopting something that will give real-world results immediately. And what I've presented here is being used across at least about 100 different customers of ours, all the way in the West, in India. We mentioned about the UAI project at IIT Bombay. That also looks at something similar in principle. Now moving to the robotic side of it. Typically, when I speak about robots, people start imagining the movies where the cars transform into, Optimus Prime. That is a lot of people's imagination of what robots are. Industrially, of course, the industrial robots have been, in play for a long, long time. They've predominantly been in applications such as palletizing, pick and place operations, assembly operations, packaging, labeling. These are some of the applications that robots are very popularly known. And automotive industry is the one that popularized the use of industrial robots. And deriving from those 6-axis robots, the advent of CAD/CAM, I think, came about with specialist applications that we felt would be transferred from very large CNC machines that were very expensive. You could not move them from one place to the other. So if it was a flexible manufacturing system that somebody was looking at and also wanted a fair amount of reasonable precision, there were these 6-axis robots which were already used for some manufacturing applications. They were then, the CAD/CAM software enabled the utilization of these by just changing the end effector tooling. Then the results are welding, coating, dispensing, even milling and additive manufacturing that we spoke of, trimming, deflashing, deburring applications, polishing, sanding, and even applying the small tools to these robots. For example, when you look at these turbine blades, the final tertiary finishing is what is called as linishing, where the robots actually hold the part and put it against the belt mechanism to remove all the burrs at the edge of things. Even here again, there are videos. I'll just quickly run through these. This is the interface where a CAD/CAM software allows the design as well as programming of such robots. Very quickly, it generates those commands into the language that can be read by these robots. And the result is what you see simulated there, being applied practically on the shop floor. So whatever was visually seen there is being manufactured here precisely as well. This was a welding example. That are passing through it in the line. Likewise, this is an example of how a car is modeled using clay. Typically, car designers are absolutely brilliant people with a lot of imagination who slap on clay onto a structure and then using a variety of tools, they shape the car's design manually. But using modern CAD/CAM systems, you can do all of that within a CAD system and then allow these robots to mill the clay part out and create a clay prototype of the automotive part in question. In this case, it's a whole car. It could be the body of a two-wheeler. It could be any such automotive component. And here, the application is for areas like, let's say, for example, film. There are various props that we see in movies. There are various props that we see in theme parks, and each of these are not structurally very precise, but the parts are very large, and it's prohibitive to manufacture them using traditional systems, and therefore robots are used to create such parts as well. Here again, this is a robot, and this is a simple lathe, and while the lathe turns, the robot is adding material onto this component to create this screw mechanism. Again, an application of additive manufacturing using robots. Examples of plasma cutting and in different orientations on a sheet metal. It turns across in 6 axis. What you're seeing here has been prior created in CAD/CAM systems, and the robot is just following the same path that was created there. Deburring and deflashing. Especially for dies. You see, this is using a grinding wheel along multiple axes, simultaneous movements, and a tabletop robot for this application. So the takeaway is that hybrid manufacturing is becoming mainstream these days. A departure from how it used to be a horizon technology a few years back. The combination of additive and subtractive, which is hybrid machining, is what is a practical form of manufacturing, which is being used and applied across various industries today. in our country and abroad. The departure of using robots just for simple pick and place applications to innovative applications, which we saw in these videos. And for all of these things, CAD CAM is the enabler because it's an offline programming system, which gives you what you see is what you get kind of an application on these different and very, very complex machineries. Thank you. And Mr. Vineet said was supposed to be here for the panel today. Regrettably, he was called away for a last minute meeting, and therefore I filled in his place. Thank you for accommodating this request, Mr. Gopal Krishna. And that's all from my side.
Thank you, Mr. Daniel, for briefing us about the advancements in hybrid manufacturing and robotic machining using modern CAD/CAM systems.